66 million years ago, the sky above every continent on Earth changed. Something entered the atmosphere and stayed there. The asteroid itself was gone in less than a minute. The darkness it created lasted for years. The sky closed, and it stayed closed. The material blocking the sunlight did not come from space. It came from the Earth itself, rock blasted from the ground and suspended high above the surface, turning the planet's own atmosphere against everything living below it. The sunlight weakened. Temperatures fell. Across land, temperatures dropped by as much as 26 degrees Celsius, about 47 degrees Fahrenheit. A planet that had never maintained permanent ice caps was suddenly experiencing freezing conditions across continents that had spent millions of years warm, and the effects reached deeper than temperature. Photosynthesis stopped. Not in one region, globally, for nearly 2 years, the process that supports almost every complex food chain on Earth was severely suppressed, with the disruption continuing for much longer afterward. Plants could no longer capture sunlight normally. The food chains built on them began to collapse. Then the losses spread upward. Around 75% of all species disappeared, not because the asteroid itself physically reached every corner of the planet, because of what the sky became afterward. The animals that survived were not necessarily the strongest, they were not necessarily the fastest, and they were not necessarily the most advanced. Many were simply already living in places where the darkness and cold could not reach them as completely. Their survival was almost accidental, but that accident changed the future of life, because when the climate eventually recovered, the world was no longer the same. The dominant animals were gone, entire ecosystems had disappeared, and the survivors were left with an Earth that was suddenly full of empty spaces. The winter had finished what the asteroid started, and the strange part is that the same darkness that killed so much life also determined which creatures would inherit the planet afterward. If these stories are what keep you coming back, take a moment to like the video and subscribe. Get comfortable, and let's step into the winter that changed the world. 66 million years ago, the continents carried ecosystems refined through geological time. Dinosaurs had occupied the planet for roughly 150 million years, allowing lineages to specialize into forms suited to forests, floodplains, deserts, coastlines, and open country. Their world had layers of life, connected through food, shelter, competition, and reproduction. The climate was warmer than the one familiar today. Global average temperatures were about 8 degrees Celsius or 14 degrees Fahrenheit, higher than modern averages. Permanent polar ice was absent. Palm trees and other warm climate plants grew at latitudes where snow and frozen ground would eventually become ordinary features of the landscape. Across North America, a shallow inland sea stretched from the Gulf of Mexico toward the Arctic, dividing the continent into eastern and western land masses. This was the Western Interior Seaway, a broad marine corridor filled with life. Mosasaurs moved through its waters as major predators, while plesiosaurs occupied other feeding roles. Ammonites drifted and swam through the marine environment in extraordinary numbers, their coiled shells marking an older cephalopod lineage. Along its margins, rivers carried minerals and organic material into the sea, linking terrestrial landscapes with marine communities. On land, dinosaur diversity had reached a remarkable degree of specialization. Horned herbivores browsed and cropped vegetation distinctly. Duck-billed dinosaurs processed plants with efficient dental batteries. Armored forms carried their own defenses, while theropods occupied predatory roles, ranging from small insect hunters to enormous apex hunters. Across the continents, species combinations produced regional ecosystems shaped by climate and geography. Far below the scale of those animals, another world operated across the ocean's surface. Coccolithophores and planktonic foraminifera formed immense communities of microscopic organisms surrounded by seawater. Their shells became part of marine sediment after death, while their living activity helped move carbon through the ocean and contributed oxygen to the atmosphere. The planet's largest animals depended, indirectly, on processes carried out by organisms too small to see without magnification. Mammals were present within this intricate system, although their lives occupied a much smaller portion of the landscape. Many were nocturnal and insectivorous, with bodies generally small enough to live among roots, leaf litter, burrows, and sheltered spaces. Their ecological roles were modest compared with those of the great reptiles around them. A mammal could pass through a Cretaceous forest without becoming part of its dominant architecture. That distinction mattered only because the architecture itself had become so complete. Every major environment supported specialists, and every specialist depended on other organisms remaining available. Plants supported herbivores, herbivores supported predators. Marine plankton fed animals at higher levels while participating in planetary chemical cycles. Decomposers returned nutrients to soils and sediments, allowing another generation of growth. Nothing about this world suggested that its structure was about to disappear. Its ecosystems had endured volcanic upheaval, shifting seas, changing climates, and smaller disruptions across millions of years. The Cretaceous world had accumulated resilience through complexity, yet that same complexity meant that countless lives were connected to conditions they could not control. Above all of it stretched the atmosphere, carrying sunlight across forests, plains, inland seas, and open ocean. Every living system described here had evolved beneath that sky and depended on its regular return of light. This was the world the asteroid found, mature, layered, and deeply interconnected, with no biological memory of a darkness capable of covering the entire planet. At the center of the Yucatan Peninsula, the ground itself became part of the catastrophe. The asteroid arrived at extraordinary speed, traveling roughly 69,000 kilometers per hour, which is about 43,000 miles per hour. Its diameter was about 11 kilometers, which is nearly 7 miles. In moments, an impact basin more than 180 kilometers wide, which is about 110 miles, was forming in fractured rock. The energy released was almost beyond ordinary comparison. Around 100 trillion tons of explosive energy were unleashed, an amount exceeding a billion Hiroshima scale explosions. The fireball, shock waves, ejecta, and returning debris transformed the surrounding landscape within minutes. The crater reached roughly 19 kilometers deep, which is nearly 12 miles, although much of that original depth was later altered by collapse and rebound. What made the impact especially consequential was the geology waiting underneath it. The Yucatan Peninsula contained thick deposits left by ancient seas, including anhydrite and gypsum, minerals rich in sulfur. The same rocks also contained abundant organic carbon. The asteroid could have struck many places on Earth, yet this particular target held a chemical mixture capable of changing the atmosphere on a planetary scale. Rock heated beyond recognition was thrown upward with the force of the collision. Fine silicate particles entered the upper atmosphere, carrying pulverized fragments of the planet itself. Their small size allowed some of them to remain suspended far above the surface, where ordinary weather could not remove them quickly. The sulfur bearing minerals followed another chemical path. Extreme heat vaporized their contents, releasing sulfur gases into the atmosphere. There, reactions involving oxygen and water transformed much of that material into sulfate particles and sulfuric acid aerosols. These particles interacted with incoming sunlight, scattering part of it away from the surface and adding another layer to the atmospheric disturbance. A third material joined them. Black carbon came from organic rich rock exposed to the impact's immense heat, while fires ignited across surrounding landscapes added further soot afterward. Soot absorbs sunlight efficiently, allowing a relatively small mass of particles to produce a large change in the amount of light reaching the ground. The three materials therefore entered the atmosphere together while behaving very differently. Silicate dust remained aloft for years. Sulfur compounds formed reflective aerosols that persisted for a shorter period. Soot acted rapidly, absorbing light and contributing to the first severe reduction in surface illumination. Their effects overlapped, creating a sequence in which one atmospheric process could continue after another had begun to weaken. Within hours, impact debris had traveled around the planet through the upper atmosphere. Particles that began above one continent were no longer confined to that region. The atmosphere became the great distributor, carrying material across oceans and land until the consequences were global. There was no boundary on the surface capable of containing what had been released above it, and no ecosystem remained outside the reach of the altered sky. The collision itself belonged to a single afternoon. The crater was already taking shape. The surrounding landscape had been transformed, and the first material was spreading through the sky. Above Earth, three distinct atmospheric agents had been loaded into circulation, each carrying a different chemical character and a different duration. The asteroid had struck the ground once. Its consequences had begun to occupy the whole atmosphere. The first hours after the collision carried an unusual sequence. The planet was struck by a wave of heat before the long cooling began. Material thrown beyond the atmosphere returned at extraordinary speed, compressed the air around it, and produced intense infrared radiation that reached the surface over a period of several hours. For animals exposed beneath the open sky, this radiation created a severe thermal burden. Body temperatures could rise toward lethal levels before the suspended debris had settled into its longer atmospheric pathways. The danger was especially severe across landscapes where there was little protection from the returning material. Open terrain offered no natural shield, while dense soil, water, and stone could absorb energy. Research into survival patterns among land vertebrates has identified this reentry heating as an important source of early mortality. The pattern carries an almost geographic logic. Animals occupying burrows, submerged environments, caves, or rock shelters had physical layers between themselves and the heat. Their surroundings absorbed or dispersed part of the incoming energy, creating a narrow advantage during an event that lasted only hours. The same heating transformed vegetation into fuel. Forests and other plant communities dried rapidly under the radiant pulse, and fires spread across portions of the continents. Their flames released additional black carbon into the atmosphere, adding material that would later influence the amount of sunlight reaching the ground. The fires, therefore, became part of the atmospheric aftermath, extending the consequences of a heat event that had already passed. Far from the impact site, another signal was moving through the crust. The collision generated seismic energy on a scale rarely encountered in Earth's geological record. Estimates place the earthquake magnitude around 10 to 11. Approximately 13 minutes after the impact, those waves reached what is now North Dakota, where they disturbed an inland waterway and generated a surge around 9 meters high, which is about 30 feet. Water swept through the channel with enough force to carry fish and sediment together. The disturbance was brief in geological terms, yet its deposits preserved a remarkable trace of the first hours. While one part of the planet was still dealing with returning heat, distant waters were responding to vibrations that had traveled through the Earth. Across the continents, the sequence was unfolding at different speeds. Radiant heating reached exposed surfaces first. Fires followed in regions where vegetation ignited. Seismic waves crossed the crust and disturbed distant waterways. Above them, the material expelled by the collision was spreading through the upper atmosphere, already changing the conditions under which every exposed ecosystem depended. Then the extraordinary heat began to fade. The fires continued in some regions, while the atmosphere retained the particles released during the collision and combustion. Surface conditions were moving away from the familiar climate of the Cretaceous, although the full transformation had only begun. By the end of that first day, the crater had formed. Distant sediments had begun recording the disturbance, and flames were adding their smoke to the atmosphere. The asteroid's passage through Earth's history had lasted moments. Its first 24 hours had already altered land, water, air, and the lives occupying all three. In the Badlands of southwestern North Dakota, a layer of rock preserves a moment that usually disappears from the fossil record. The site, called Tanis, lies within the Hell Creek Formation, and its sediment accumulated during the hours surrounding the impact. Instead of presenting a broad geological interval, it holds a compressed record of an afternoon when water, animals, and falling debris converged. The deposit is roughly 1 meter thick, which is about 3 feet. Within it, hundreds of freshwater fish were caught together as a surge moved through an ancient inland waterway. The disturbance began when seismic waves from the impact traveled through Earth's crust and reached North Dakota roughly 13 minutes later. The resulting seiche, a large sloshing movement of water, pushed a surge upstream, carrying fish and sediment into the channel. Paddlefish and sturgeon were swept into the flow. Their bodies became arranged in orientations consistent with rapid burial, with many preserved almost vertically inside the sediment. The speed of deposition mattered. A gradual accumulation of mud could scatter remains and allow bodies to settle naturally. Tanis instead records animals overwhelmed during a brief disturbance, then sealed into the growing layer before currents could rearrange them. Among the most delicate evidence are tiny glass beads lodged inside the gills of some fish. These are microtectites, droplets of molten rock produced when the impact melted material from the ground and sent it high into the atmosphere. As those droplets cooled, they hardened into glass and began falling across distant parts of the planet. Some reached the water above Tanis while fish were still alive. The beads entered their gill chambers as the animals breathed, creating a connection between the atmosphere above North Dakota and living bodies below it. The impact had occurred thousands of kilometers away, yet its ejecta had arrived over a freshwater ecosystem within the same hour. Their final moments are preserved with unusual intimacy. A fish could still be breathing while particles, born from a distant impact, descended through the atmosphere. Water carried those particles into the same place where the animals were moving, joining an astronomical event to the ordinary rhythm of an inland ecosystem. The sediment also preserves another chemical marker. Above the fish-bearing layer lies clay enriched in iridium, an element uncommon in Earth's crust, but more abundant in extraterrestrial material. The same unusual enrichment appears at the geological boundary separating the Cretaceous from the Paleogene in locations around the world. At Tanis, its position provides an additional link between the fossil deposit and the global impact horizon. What makes the site valuable is the unusual combination of evidence held together in one place. Fish remains, rapid sedimentation, impact glass, and the iridium-rich boundary occur in a sequence that preserves the event at humanly imaginable timescales. Geological processes usually compress years, centuries, or millennia into layers too broad to distinguish individual moments. Here, the record narrows toward an afternoon. Research surrounding Tanis continues, and individual interpretations remain under examination. The broader evidence, including impact spherules associated with fish gills and the overlying iridium enrichment, has given scientists an unusually direct view of the earliest stage of the catastrophe. The fish preserved at Tanis never encountered the long darkness that followed. Their world changed above them first, through falling glass and disturbed water, while their bodies became part of a sedimentary record that would remain in the ground for millions of years. At first, the atmosphere carried a substance that behaved less like falling ash and more like a veil. Soot rose high above the weather systems, where sunlight could encounter it before reaching forests, fields, and ocean surfaces. Its importance came from its ability to absorb incoming light, converting part of that energy into heat within the atmosphere while leaving much less illumination available at ground level. Some of this black carbon came directly from the organic rich rocks struck by the asteroid. The collision heated those materials to extraordinary temperatures and lofted their carbon rich remnants upward. This meant that the first soot did not depend on forests burning across distant continents. It had already been placed into the upper atmosphere by the impact itself. That distinction changes the rhythm of the first darkness. Wildfires became another major source after the returning heat ignited vegetation, and their smoke added to the atmospheric burden. Their contribution unfolded across days and weeks. Impact-generated soot had already begun its journey around the planet within hours, carried through the stratosphere by powerful winds. Before many distant landscapes had even begun burning, the upper atmosphere was already receiving material capable of absorbing sunlight. The effect on illumination was profound. Climate simulations indicate that soot produced the fastest and strongest reduction in surface light among the major particulate materials released by the collision. Within weeks, photosynthetically active radiation, the portion of sunlight used by plants and microscopic ocean organisms, had fallen toward almost nothing across much of the planet. For plants, the distinction between dim light and usable light mattered enormously. Leaves can continue existing for a time after their energy supply is reduced, drawing on stored reserves. Growth requires a continuing source of energy, however, and that source was disappearing from the surface. In the ocean, phytoplankton faced an even narrower margin. Their world existed close to the sunlit surface, where food production depended directly on incoming radiation. The sky itself would have changed in appearance. Direct sunlight became extraordinarily weak, leaving the daytime atmosphere under a diffuse gray illumination. Shadows would have lost much of their former strength. Landscapes that had been shaped by bright tropical and subtropical light were receiving only a fraction of the energy their ecosystems had evolved to use. Cooling accompanied the loss of sunlight. Less radiation reached the surface, while soot remained suspended high above the ground. The first decline in temperature therefore began during the same period in which biological production was collapsing. These changes reinforced one another. Plants captured less energy, food became scarcer, and the surface lost more of the warmth supplied by sunlight. Soot did not remain forever. Particles were gradually removed from the atmosphere through chemical processes and gravitational settling, with much of the initial burden disappearing over months to a few years. Its influence was therefore concentrated in the earliest and most severe phase of the atmospheric disturbance. During that interval, the planet's surface received so little usable sunlight that the ordinary rhythm of growth was interrupted on a global scale. The darkness had arrived through material born from the collision itself, then strengthened by fire. Above the recovering continents and oceans, the atmosphere had become a filter between Earth and its star, changing the amount of light that could reach every leaf and every sunlit layer of water. A difference, measured in micrometers, became one of the most important details in the length of the impact winter. The silicate particles produced by the collision were extraordinarily fine, much smaller than earlier climate models had assumed. Their dimensions changed how long the material could remain suspended above the surface. Measurements from the Tanis boundary deposit indicate that many of these particles were between zero point 0.8 and 8 micrometers across. A human hair is roughly 70 micrometers wide, making these grains several times to many times thinner than a single strand. At this scale, gravity still pulls downward, yet the surrounding atmosphere exerts enough drag to slow their descent dramatically. That physical difference reshaped the timeline. Coarser fragments fall relatively quickly, settling through the atmosphere over days or weeks. Fine silicate dust can remain aloft much longer, especially after reaching the stratosphere, where there is little rain to wash it from the air. The particles therefore became persistent residents of the high atmosphere, moving with global circulation rather than returning immediately to the ground where they originated. Climate simulations using these measured particle sizes produced a striking result. The silicate dust could remain influential for approximately 15 years. Its contribution to global cooling may have lowered average surface temperatures by as much as 15 degrees Celsius or 27 degrees Fahrenheit. Such a change transformed the energy balance of a planet whose ecosystems had developed under a much warmer climate. Light remained the deeper problem. The dust scattered and absorbed incoming radiation, reducing the amount of photosynthetically active light available to plants and microscopic ocean organisms. Simulations indicate that this usable light could have fallen close to zero for almost 2 years, while substantial suppression continued beyond that interval. For a leaf, a dimmed sky meant less energy available for growth. Across the ocean surface, the same reduction reached organisms whose entire existence depended on sunlight. The impact winter, therefore, had a duration measured in years, while its biological effects accumulated through countless small failures of growth, feeding, reproduction, and renewal. The persistence of the dust also explains why atmospheric recovery could not begin as soon as the first soot disappeared. Different particles occupied different layers of the atmosphere and followed different physical pathways. Soot declined relatively quickly. Sulfate aerosols also diminished over a shorter span. Fine silicate grains remained suspended after those materials had begun to leave, extending the period of reduced illumination and cooling. There was no clean boundary between one atmospheric phase and another. The planet moved through overlapping influences, with the fine mineral dust maintaining a long presence above the surface. Each particle was tiny enough to be almost meaningless on its own, yet together they altered the amount of energy reaching forests, lakes, rivers, and oceans across the globe. The source of this prolonged veil was deeply terrestrial. The material had been part of Earth's crust before the collision shattered and vaporized it. Rock from the ground had entered the sky, where its smallest fragments became capable of remaining aloft for years. The planet had effectively lifted pieces of itself into the atmosphere and placed them between its living surface and the sunlight that sustained it. That persistence gave the winter its unusual duration. The first darkness faded with time, while the mineral suspension continued altering the climate, extending the disruption across many growing seasons. Rain became part of the atmospheric aftermath in a way that reached places the high atmosphere could not touch directly. The sulfur released by the collision eventually returned toward the surface, carried through clouds and precipitation. Its origin was buried in the rocks beneath the Yucatan Peninsula, where minerals formed from evaporating seas had stored sulfur for millions of years. Anhydrite and gypsum are calcium sulfate minerals that accumulated when ancient marine waters repeatedly evaporated. The impact converted these deposits into vapor and injected sulfur gases high into the atmosphere. Sulfur dioxide and sulfur trioxide rose into the stratosphere, where chemical reactions transformed much of the sulfur into sulfate aerosols. These particles were extremely small, yet they occupied an important position above the weather systems. Sulfate aerosols reflect incoming sunlight, sending part of that energy back toward space before it can warm the surface. Their presence therefore deepened the cooling already developing around the planet. The atmosphere had gained another layer capable of changing the balance between sunlight arriving and heat remaining near the ground. Water vapor provided the next step. Chemical reactions involving sulfur compounds produced droplets containing sulfuric acid, which could spread through the stratosphere and eventually descend through precipitation. Their distribution was global, and geological sediments from widely separated regions preserve chemical evidence of the disturbance. The same atmospheric event left related sulfur signatures across continents and ocean basins. As the acidic material reached the surface, shallow environments were especially vulnerable. Rivers, ponds, lakes, and coastal waters contain less chemical buffering than the deep ocean. A change in acidity could therefore alter conditions for organisms whose bodies and food sources depended on a narrow chemical range. Freshwater systems already facing reduced sunlight and falling temperatures now received another environmental pressure through their water. Land vegetation encountered the chemistry from above and below. Acidic precipitation could leach nutrients from soils, making essential minerals harder for roots to obtain. Plant tissues exposed to acidic water could also be damaged, while soils already affected by the loss of vegetation became more vulnerable to erosion. Rain no longer represented only a return of water to the ground. Its chemical character had changed. The sulfur disturbance also reached the upper atmospheric chemistry surrounding the ozone layer. Reactions involving sulfur and nitrogen compounds altered the balance of gases that protect Earth's surface from ultraviolet radiation. As the particulate veil began thinning at later stages, periods of increased ultraviolet exposure could have added another burden to organisms attempting to resume growth. Sulfate aerosols were persistent enough to matter for years, yet they did not share the extraordinary longevity of the finest silicate dust. Precipitation gradually removed them from the atmosphere, allowing their influence to weaken. Their passage, therefore, occupied an intermediate place in the atmospheric sequence, longer than the most acute soot phase and shorter than the mineral dust that remained aloft for many years. For the living world below, these layers overlapped in time. Reduced sunlight, limited energy production, cooling altered habitats, and sulfur changed the chemistry of rain and surface waters. Each pressure reached life through a different pathway, while together they reshaped the physical conditions under which ecosystems could continue operating. The effect was especially persistent where rainfall carried dissolved acidity repeatedly through the same soils and waterways. Each episode could remove another portion of the chemical balance that living communities had depended upon for generations. There is a season preserved inside the bones of fish that died on the day the world changed. At Tanis, their fossilized skeletons retain microscopic patterns of growth, allowing researchers to place the Chicxulub impact within the yearly rhythm of life. The evidence points to spring in the Northern Hemisphere, a detail established through work published in 2021. Fish bones grow in layers as conditions around them change. Periods of abundant food and active metabolism leave different structures from periods when growth slows. The pattern resembles the information preserved in tree rings, although the record here is written on a much smaller scale. In the Tanis fish, the outermost growth features indicate a period of rapid seasonal development. Their bodies were actively growing when the impact arrived. That timing places the catastrophe in Northern Hemisphere spring. Across forests, wetlands, rivers, and plains, this was a season of renewed biological activity. Many plants were beginning another cycle of growth after the resources stored from the previous year had been drawn down. The fresh season had started, but its new energy had not yet accumulated into a reserve capable of carrying ecosystems through prolonged hardship. For animals, spring also brought reproduction, nesting, egg laying, hatching, and the arrival of young were woven into the seasonal calendar of countless species. A world filled with developing offspring contained many lives that had only recently entered their most demanding stages. Their survival depended on food becoming available at the same time that adults were spending energy on growth, migration, courtship, and care. The timing carried a different weight south of the equator. While northern ecosystems were entering spring, southern hemisphere ecosystems were moving into autumn. Plants were approaching the end of their productive season, and many animals were entering a period when food availability would naturally decline. The impact winter, therefore, arrived as seasonal cooling was already beginning. The biological year was turning toward scarcity when the atmosphere imposed an entirely new burden. This contrast matters because ecosystems are not static arrangements of species. Their resilience changes with the calendar. A population entering winter with stored energy has a different chance of enduring prolonged darkness than one beginning reproduction after a period of depleted reserves. A plant community at the start of growth has different resources available than one near the end of its productive cycle. The same atmospheric disturbance could therefore meet different biological conditions across the planet. None of this means the asteroid selected its moment. The collision followed the mechanics of celestial motion, indifferent to nesting seasons, plant growth, or food reserves. Yet the date happened to intersect with a particularly sensitive point in Earth's biological calendar. The catastrophe arrived when northern life was beginning again, and southern life was preparing to contract. The season is therefore more than a detail attached to the extinction. It is a small temporal mark inside a planetary disaster recovered from the growth of animals that lived for only a brief moment longer. Their bones preserve the rhythm of spring, the final trace of ordinary growth before the biological record breaks abruptly at the edge of another season. More than 66 million years later, that interruption allows the timing of the impact to be read with an intimacy that rocks alone could never provide. Photosynthesis had no substitute. Across the surface of the planet, living systems depended on the steady conversion of sunlight into chemical energy, and when usable light vanished, the first losses appeared at the smallest scales. Phytoplankton were especially exposed. These microscopic organisms drifted through sunlit ocean waters, turning light and carbon dioxide into the organic matter that supported enormous communities above them. With photosynthetically active radiation reduced to near zero, their growth collapsed. Some could persist as dormant cells or through stored nutrients, yet the broad production that sustained marine food webs had been interrupted. The change moved upward through the water column. Zooplankton depended on phytoplankton for food, and many small fish depended on zooplankton. Larger fish and marine reptiles depended on those smaller animals. Each connection carried the shortage farther from its source. A predator could survive for a time after its prey became scarce, drawing on stored energy, but that reserve could not restore a food web whose primary production had stopped. Land ecosystems possessed a little more delay. Plants had roots, seeds, underground tissues, and stored carbohydrates that could carry some individuals through unfavorable conditions. Forests did not vanish in a single moment. Their leaves and growing shoots, however, depended on returning light. As the darkness persisted, photosynthetic production declined, then weakened the supply of fresh plant material entering terrestrial food chains. Large herbivores occupied an especially difficult position. Their bodies demanded enormous quantities of vegetation every day, and their digestive systems were adapted to diets that could not be replaced easily. A giant sauropod needed hundreds of pounds of plant matter each day. When living vegetation became scarce, there was little flexibility available at that scale. A small mammal could search for seeds, insects, fungi, or decaying material. A huge herbivore had far fewer choices. Carnivorous dinosaurs inherited the same problem from another direction. Their immediate food consisted of animals, yet those animals depended heavily on plants or on smaller creatures that depended on plants. As herbivore populations weakened, predators encountered an expanding shortage. Hunting skill could not create prey where primary production had failed. Body size had once offered major advantages. Large animals could travel farther, store substantial energy, and dominate ecological spaces with relatively few competitors. During prolonged food scarcity, those same characteristics became costly. Every additional kilogram of living tissue, which is about 2.2 pounds, required energy to maintain, while the landscape was producing less of the energy needed to sustain it. Small animals occupied a different biological position. Many required less food, reproduced more rapidly, sheltered in burrows or protected spaces, and could exploit resources that remained outside the collapsing plant-based pathways. Seeds, insects, fungi, carrion, and detritus offered scattered sources of energy. None guaranteed survival, yet together they created several possible routes through the shortage. The food web, therefore, began failing from its foundation. The darkness did not need to reach every organism directly. It only needed to interrupt the process that transformed sunlight into usable energy. Once that conversion weakened across oceans and continents, the consequences traveled through predators, herbivores, scavengers, and decomposers alike. The collapse followed the architecture of life itself, moving upward from the smallest producers toward the largest bodies that had once seemed so securely established. Every missing meal became another link removed from the chain. The phrase "Strangelove Ocean" describes a strange condition in the marine world after the impact, when seawater continued to circulate and exchange chemicals while much of the life at its sunlit surface had vanished. The ocean still moved through currents, tides, and sinking waters. Its chemistry remained active. Yet the biological activity that had once filled the upper ocean had been reduced to a fraction of its former abundance. Before the catastrophe, the surface waters supported dense communities of coccolithophores and planktonic foraminifera. These microscopic organisms lived near the boundary between sunlight and seawater, building delicate calcium carbonate shells as they grew. Their bodies became part of a vast living network that connected sunlight, nutrients, carbon dioxide, and marine animals. The surface was productive on a planetary scale, with countless organisms transforming light into new organic matter. That system was especially vulnerable when the sky darkened. Coccolithophores declined sharply, while planktonic foraminifera suffered one of the most severe losses recorded among marine groups at the extinction boundary. Their disappearance mattered far beyond the organisms themselves. Many animals depended on them directly or indirectly, and their remains had also formed an important pathway by which material moved from the surface toward deeper water. This downward movement is known as the biological pump. Tiny organisms absorbed carbon dioxide near the surface, and when they died, their remains could sink through the water column. Some of that material reached the deep ocean, carrying carbon away from the atmosphere for long periods. When surface productivity collapsed, that transfer weakened as well. The ocean continued processing chemicals, but one of its major biological routes for moving carbon had been interrupted. The change can still be read in marine sediments. Carbon isotope measurements preserve a chemical pattern consistent with an enormous reduction in surface productivity. Similar evidence appears across widely separated ocean basins, showing that the disruption was planetary rather than confined to one coastline or current system. The sediment record turns an invisible biological collapse into something that can be measured millions of years later. Life on the seafloor initially occupied a different position. Bottom communities could feed on organic material that had accumulated earlier or continued arriving from the surface for a time. Their circumstances therefore changed more gradually. As the supply from above diminished, however, the deep ocean received less nourishment. The biological connection between surface and seafloor weakened layer by layer. Recovery required far longer than the disappearance itself. Surface plankton communities took roughly 3 to 4 million years to regain anything close to their former diversity. The returning ocean was therefore not a restored copy of the one that had vanished. Evolution had reshaped the surviving lineages, while ecological space opened for new combinations of organisms. The Strangelove Ocean captures this distinction with unusual precision. Water could keep circulating without interruption. Minerals could continue reacting, settling, and dissolving. Currents could carry heat and dissolve substances across entire basins. The machinery of the ocean remained in motion, while its surface biological engine had largely failed. It was a functioning water world whose most productive layer had been emptied, leaving chemistry to continue where life had once dominated. For a time, the deep sea received the memory of that lost productivity only as a thinning rain of organic particles. Each fragment carried traces of a surface ecosystem that was becoming harder to sustain. As those particles grew scarce, organisms accustomed to steady supplies faced a new ocean, one where energy arrived less often and in smaller amounts. The change spread downward without requiring the water itself to become lifeless. The sea had become a place where circulation outlasted abundance, and where the chemistry of water continued its ancient cycles after the surface communities that shaped them had nearly disappeared. Freshwater habitats occupied a narrow space between land and sea, and after the impact, that position became unusually important. Lakes, rivers, ponds, and coastal estuaries carried far less dissolved material than the deep ocean, leaving them with limited chemical buffering. When acidic precipitation began falling, these smaller waters could change rapidly. High above the surface, sulfur released by the impact had formed sulfate aerosols that eventually returned through precipitation. Extreme heat around the impact also produced nitrogen oxides, which entered the atmospheric chemistry surrounding the catastrophe. Together, these processes contributed to rainfall containing sulfuric and nitric acids. The precipitation reached watersheds already struggling with darkness, cooling, and declining biological production. The deep ocean possessed enormous chemical reserves and an immense volume of water. Its dissolved minerals could absorb and neutralize substantial amounts of incoming acidity without producing an immediate transformation throughout the entire basin. A shallow pond possessed nothing comparable. Its chemistry could shift within a much smaller volume, allowing repeated acidic rainfall to push conditions beyond the tolerances of many organisms. Rivers faced another complication because their waters were continually connected to the surrounding landscape. Acidic precipitation moved through soils and rock, carrying dissolved minerals toward streams and lakes. Vegetation suffered along the same pathways. Nutrients were stripped from soils, plant tissues were damaged, and root systems encountered changing chemical conditions at a time when reduced sunlight was already limiting growth. Coastal estuaries occupied an intermediate position. They received fresh water from rivers while remaining connected to marine environments, producing chemical conditions that could fluctuate with tides, rainfall, and sediment movement. Their communities were therefore exposed to several forms of disruption at once. The boundary between land and ocean became a zone where changing chemistry could accumulate from multiple directions. The atmosphere carried another complication. Impact-related chemical reactions damaged the ozone layer, reducing some of its protection against ultraviolet radiation. Whenever enough particulate material cleared to permit greater sunlight at the surface, surviving organisms could therefore encounter radiation conditions different from those before the catastrophe. Recovery from darkness did not necessarily mean a return to familiar light. Rocks around the world preserve traces of these changes. Chemical alterations within boundary sediments record intensified weathering and the movement of dissolved material from continents toward coastal waters. The signatures occur across widely separated regions, showing that altered precipitation and erosion were part of a planetary environmental disturbance rather than an isolated local event. Freshwater communities, however, produced an unexpected pattern. Their extinction rates were comparatively low in many groups when measured against the enormous losses experienced elsewhere. The reason reaches deep into their evolutionary history. Freshwater environments naturally fluctuate. Water levels rise and fall. Temperatures change sharply. Oxygen concentrations vary, and dissolved minerals can shift with rainfall and evaporation. Organisms living in such habitats had already encountered unstable conditions as part of ordinary existence. That history offered an accidental advantage. Species accustomed to changing chemistry could possess greater tolerance when acidic precipitation altered their surroundings. Animals capable of surviving periods of limited food or oxygen also carried traits suited to a world where resources had become unreliable. Their resilience had been shaped by repeated environmental variation long before the asteroid arrived. The contrast reveals something important about extinction. A stable environment can support extraordinary specialization, allowing ecosystems to become intricate and highly productive. Yet, specialization can narrow the range of conditions a species can tolerate. Freshwater life had evolved amid instability, and that difficult background became an unexpected source of endurance when the planet itself became unstable. The survivors were sometimes those already accustomed to living with uncertainty. The climate of the late Cretaceous had offered life a long familiarity with warmth. Ice sheets were absent from the poles. Tropical conditions reached far into higher latitudes, and ocean temperatures varied within a comparatively narrow range. Across generations beyond counting, organisms had evolved inside that broad envelope. Their bodies and behaviors carried the imprint of a world where prolonged freezing was largely absent. Even ecosystems near the poles had developed within a climate far removed from the sustained cold now spreading across continents. Cold, therefore, arrived as more than a change in temperature. It introduced conditions for which many species had no established biological response. Animals could adjust to ordinary seasonal shifts, yet seasons had limits. A winter lasting for years required different strategies, including prolonged dormancy, reduced activity, altered feeding behavior, and ways of conserving energy when food remained scarce for far longer than a normal season. Climate simulations indicate that temperatures across land may have fallen by as much as 47 degrees Fahrenheit. Some continental regions reached conditions below the freezing point, while cold desert, tundra, and ice cap like environments spread across areas that had previously supported forests and warm adapted ecosystems. During the first 1 to 3 years, climate zones changed with a speed and scale that left little time for ecological adjustment. The change reached the oceans as well. Sediments from Texas preserve evidence of a pronounced cooling episode in surface waters after the impact. Ocean temperatures did not remain insulated from the atmospheric disturbance. Their decline affected circulation, dissolved gases, nutrient movement, and the organisms living near the surface, extending the disruption into environments that had seemed separated from the catastrophe above. Rainfall changed with the cooling atmosphere. As evaporation weakened and vegetation declined, many river systems became less predictable. Forest roots had once helped bind soil together, but widespread plant loss left exposed ground vulnerable to erosion. Sediment moved more readily into streams and coastal waters, altering habitats, while the biological communities that depended upon them were already shrinking. For an animal moving through those first months, the altered world would have been difficult to recognize. Daylight remained present, yet the sky offered little brightness. The surface stayed under a persistent gray cover, while cold gathered across the land and green vegetation became increasingly scarce. There was no familiar seasonal rhythm to mark the disturbance as temporary. That distinction matters because organisms do not inherit knowledge of future climates. Evolution equips populations through traits shaped by earlier conditions, and the late Cretaceous had provided little opportunity to develop defenses against years of severe cooling. A species could tolerate a cold night, a seasonal frost, or a short food shortage without possessing the capacity to withstand a prolonged planetary winter. Those brief stresses allowed recovery between difficult periods, while the impact removed that interval of recovery. Small differences in physiology and behavior consequently became important. Animals capable of lowering their energy demands, sheltering in protected places, eating varied foods, or surviving on stored resources had more room to endure. Species tied to abundant vegetation, stable temperatures, or continuous feeding faced a narrower path. The impact winter was therefore severe in two connected ways. It pushed temperatures beyond familiar boundaries while removing the environmental patterns that had shaped life for millions of years. Cold itself became a new ecological force, and the world offered almost no biological precedent for meeting it. From the ground, the impact winter would have looked less like a dramatic landscape and more like a familiar earth stripped of its rhythm. Forests that had once formed layered canopies became broken structures of dead trunks and branches. In many places, roots remained in the soil, but the living architecture above them had collapsed. There were no fresh leaves returning with the season, no steady renewal of the canopy, and no dependable harvest of sunlight. Across continental interiors, conditions could resemble cold desert landscapes. Precipitation had diminished, temperatures approached freezing or fell below it, and biological activity at the surface became sparse. Soil remained, rivers remained, and scattered organisms endured, yet the productive systems that had connected plants, herbivores, and predators were greatly reduced. The land still possessed its familiar shapes, though the living layer covering those shapes had thinned. The disappearance of large animals changed more than the food web. It changed the physical experience of moving through the landscape. For millions of years, enormous herbivores had broken vegetation, opened paths, trampled ground, redistributed nutrients, and carried seeds across long distances. Predators followed their movements. Their absence removed a whole layer of ecological motion. A world once organized around bodies of extraordinary size became dominated by creatures whose demands were smaller and more flexible. Rivers also carried the imprint of the collapse. Without extensive root networks binding soil, erosion increased, sending greater quantities of sediment into waterways and coastal environments. Channels could shift, banks became less stable, and the boundaries between land and water changed. The landscape was being reshaped through ordinary physical processes that had gained new force because so much vegetation had disappeared. At the ocean surface, the biological abundance of earlier times had largely drained away. Plankton blooms became scarce, feeding activity diminished, and the surface food web lost much of its former density. Cold water moved under the gray atmosphere, while the upper ocean carried far less living material. The sea continued circulating through currents and tides, yet its surface communities had been profoundly reduced. For the animals that remained, the disappearance of giant predators altered the meaning of size. Small mammals, reptiles, birds, insects, and other adaptable creatures could occupy spaces that had once been dominated by larger competitors. Being small required less food and allowed greater flexibility when resources were scattered. The ecological landscape had become a place where modest needs could matter more than physical dominance. Dead organic material became one of the most abundant resources. Leaves, wood, roots, carcasses, and other remains accumulated across land and water, creating an enormous supply for organisms able to consume decay. Detritivores and decomposers became important links in a food web built from what the previous ecosystem had left behind. Fungi were especially prominent. Fossil evidence shows pronounced fungal increases in sediments associated with the extinction boundary, reflecting the immense pulse of decomposition that followed widespread biological death. The forest floor, river margins, and coastal sediments became sites of transformation as microbes and fungi processed material that had once belonged to living ecosystems. This was the winter from within, a world still recognizable in its mountains, rivers, soils, and seas, yet profoundly altered in its living texture. Earth had not stopped functioning. It had become an environment where decay carried much of the biological activity. While surviving, life persisted among the remains of a richer world. Survival at the extinction boundary followed no grand hierarchy. The animals that endured were often those whose ordinary lives happened to fit the strange conditions created by the winter. Small bodies required less food. Flexible diets allowed a shift from living plants and prey toward insects, seeds, carrion, fungi, and other scattered resources. Burrows and sheltered spaces offered protection from changing temperatures. These traits had evolved for ordinary ecological pressures, yet they became valuable when ordinary conditions disappeared. Body size mattered because every animal carried an energy budget. A giant herbivore needed enormous quantities of vegetation each day, while a small mammal could persist on far less. When productive plants vanished, that difference became decisive. An animal capable of lowering its activity or entering dormancy could stretch limited reserves across difficult periods. Their advantage was practical rather than dramatic. A burrow could provide insulation, a varied diet could bridge one failed food source to another, and a low metabolic rate could turn a short supply into a longer one. In a collapsing ecosystem, those small efficiencies accumulated until they separated persistence from starvation. Where an animal lived mattered almost as much as what it ate. A study published in 2021 found strong evidence that ground dwelling mammals were more likely to survive than tree dwelling forms. Life among branches had offered food and shelter during ordinary times, yet the impact transformed that habitat. Heat reached exposed environments, vegetation declined, and the later cold settled across landscapes where trees could no longer provide their former protection. Animals already living near the ground could retreat into soil, leaf litter, crevices, and other buffered spaces. Diet provided another advantage. Insects could continue feeding on decaying material, fungal growth, and detritus after plant productivity collapsed. Their own food sources were tied to decomposition, which meant that the death of the old ecosystem created resources for organisms adapted to consuming what remained. Mammals capable of eating insects, seeds, carrion, and other foods therefore possessed several routes through a landscape where any single resource could disappear. Among birds, survival followed a related pattern. The lineage that produced modern birds included many ground-dwelling, diet-flexible forms. Other avian groups disappeared. Birds that could function without forests and abundant food entered the following ages with a different starting point, shaped by bodies and behaviors suited to scarcity. Freshwater ecosystems offered another refuge of opportunity. Fish and other freshwater animals lived within food webs that received substantial organic material from surrounding land. Even when sunlight could no longer sustain plant growth, dead leaves, roots, insects, and other material continued entering rivers and lakes. Turtles, snakes, lizards, and amphibians also possessed traits that reduced their energy demands and allowed periods of inactivity. Their tolerance for fluctuating chemistry gave them another measure of resilience. Many survivors occupied ecological margins long before the catastrophe. They were small, adaptable, ground-dwelling, or accustomed to consuming resources that larger specialists overlooked. Those characteristics had evolved for ordinary problems, yet remained useful when the ecological setting changed. The boundary, therefore, preserves an unexpected lesson about dominance. In a stable world, specialization and large size can support extraordinary success. When conditions shift beyond the range that shape those traits, the same advantages can become burdens. The animals that endured were often those with fewer demands, broader choices, and more places to retreat. Survival belonged less to the most powerful than to the organisms whose lives could continue when almost everything familiar had vanished. A crocodilian body can seem almost out of place in the aftermath of a global catastrophe. These animals had already occupied Earth for a long stretch of geological time, carrying a design suited to rivers, lakes, wetlands, and coastal margins. During the late Cretaceous, crocodilian relatives were diverse and widespread, with some forms adapted to habitats far removed from the familiar, modern image of a riverbank hunter. Their persistence across the extinction boundary therefore presents a biological puzzle with an unexpectedly practical dimension. The catastrophe changed the value of energy itself, making restraint a powerful survival trait. Temperature governs much of their energy economy. Crocodilians are ectothermic, meaning their body temperature depends largely on surrounding conditions, and their metabolism can fall substantially as temperatures decline. That relationship became useful when food became scarce. A warm-blooded predator must continually spend energy maintaining its internal temperature, even when prey is difficult to find. A crocodilian can reduce its activity and endure long intervals with little or no food, drawing on stored energy while its surroundings remain cold. That capacity for fasting matters when an ecosystem loses its productivity. Large predators depend on repeated meals because their bodies consume energy at a high rate. Crocodilians can wait. Their lives can be sustained through periods when feeding opportunities become widely separated. A carcass, a fish, or another small source of nourishment can become valuable across a much longer interval when daily energy requirements are low. Water offered another advantage. Aquatic environments respond to changes in air temperature more gradually than exposed land surfaces, giving crocodilians access to places where thermal conditions could remain comparatively buffered. Rivers and wetlands were deeply disrupted, yet aquatic systems retained pathways for nutrients and organic material after terrestrial productivity collapsed. A crocodilian living at the boundary between water and land could draw upon both environments without depending entirely on either one. Their behavior may have added another layer of resilience. Crocodilians can reduce movement and activity during unfavorable conditions, entering prolonged periods of reduced metabolic demand. Such states are not identical to true hibernation, and the exact behavior of extinct species during the impact winter cannot be observed directly. Fossils reveal survival, while physiology helps explain why survival was plausible. Even with these clues, scientists do not regard the crocodilian case as completely solved. The fossil record establishes that some crocodilian lineages cross the extinction boundary, while many other large reptiles did not. Their survival cannot be assigned to one protective trait. Temperature tolerance, fasting ability, aquatic refuge, behavioral flexibility, and access to food likely work together, each reducing a different part of the ecological burden. There is something almost architectural about that combination. The crocodilian body was energetically economical, physically durable, and closely connected to water. Traits that had served these animals through ordinary environmental fluctuations became useful on a planetary scale when familiar food webs failed. Their success was therefore less about superiority than compatibility with scarcity. The great predators of the late Cretaceous had bodies built for abundance, pursuit, growth, and constant access to energy. Crocodilians carried a different economy. When abundance disappeared, that economy became an unexpected advantage. Survival favored an animal that could spend less, wait longer, and remain close to water, while the larger world around it changed. The first mammals of the impact winter would have been easy to overlook. Small bodies moved through soil, leaf litter, and narrow spaces beneath the surface, while the larger world above lost its familiar rhythm. Most Cretaceous mammals were tiny by comparison with the dominant animals around them, and many lived on insects or mixed diets. Their modest needs became an unexpected advantage when food became scarce. A burrow offered more than shelter. Soil could buffer rapid changes in temperature, shielding an animal from the most intense effects that followed the impact and from some of the cold that settled over the surface afterward. For a creature with a low metabolic demand, every saved unit of energy mattered. A mammal that required only a small meal could continue where an animal needing enormous quantities of vegetation could not. The food available underground was also changing. Dead plants, fallen organic material, fungal growth, and insects formed a detritus-based network that remained connected even after photosynthetic productivity collapsed. Fungi could consume the abundance of newly dead material. Insects fed on fungi and decaying matter. Small mammals could then feed on those insects, creating a chain sustained by decomposition rather than fresh plant growth. This was a narrow economy, yet it possessed an important quality. It did not depend entirely on sunlight arriving that day. Energy captured by living plants before the catastrophe could continue moving through organisms after the plants themselves had died. Each step became smaller, slower, and more limited, but the pathway remained usable for animals whose requirements were equally small. Their reproductive biology added another advantage. Many small mammals could produce offspring more rapidly than large animals, allowing populations to respond when conditions began improving. That flexibility mattered as the environment gradually became less hostile. The mammals did not need to reclaim the world immediately. They only needed enough individuals to persist through the interval when ecological space was opening. The fossil record gives a glimpse of what followed. Plesiadapiforms, an early group of mammals related to the ancestry of primates, appear in rocks deposited within roughly 150,000 years after the extinction boundary. Their presence marks part of a broader radiation into ecological roles that had previously been occupied by other animals. The transformation was gradual, measured in generations rather than moments. For the mammals living through the harshest years, none of this had meaning. They had no knowledge of extinction boundaries or changing ecosystems. A tunnel was a place to rest, an insect was food. A fungus-covered fragment of organic material was another source of nourishment. Their survival came through ordinary behavior, repeated under extraordinary conditions. The irony rests in the scale of their lives. Traits that had kept these mammals small, adaptable, and easy to overlook had also kept their energy requirements within reach of a damaged ecosystem. Burrowing reduced exposure. Flexible diets widened their options. Small bodies reduced the cost of every movement and every breath. Those qualities did not make them dominant during the Cretaceous. They made them capable of remaining when dominance itself had become impossible. From that narrow thread of survival came millions of years of diversification. Much later, among those expanding mammalian branches would appear forms with larger bodies, different diets, and new ways of moving through the world. Their story began with animals whose greatest advantage was needing very little. The first green growth after the impact did not resemble a recovering forest. It began as a botanical foothold, recorded in layers of rock where fern spores suddenly become extraordinarily abundant. Across widely separated parts of the world, this fern spike appears close to the same geological horizon, making it one of the clearest biological signals associated with the extinction boundary. Ferns possessed an advantage suited to a damaged planet. They reproduce through spores, tiny reproductive cells that can travel across exposed ground and establish new growth without seeds, flowers, pollinating insects, or the elaborate partnerships required by many flowering plants. Their life cycle allowed them to occupy places where soil had been disturbed, vegetation had burned, and established plant communities had disappeared. The pattern preserved in the rocks is striking. Above the thin layer associated with the impact, fern spores can become so abundant that they dominate the plant material being deposited. This does not mean that every landscape became a dense fern meadow. It records a biological opportunity appearing across many regions at once, as surviving spores found surfaces with little competition and enough returning light to begin growing. Their arrival also marks a subtle change in the atmosphere above the ground. The fine particles suspended after the impact gradually diminished, allowing more photosynthetically active radiation to reach the surface. Light returned before abundance did. A plant could begin the process of rebuilding organic matter, even while the broader ecosystem remained severely damaged. The first fern communities were likely low and patchy, spreading across open terrain rather than recreating the towering vegetation of the earlier world. Their presence changed the surface in small ways. Moisture could be retained around new growth, exposed soil gained living cover, and decomposing material began entering a renewed cycle of biological activity. Each patch created another place where insects and other small organisms could feed, turning damaged ground into the earliest pieces of a renewed living landscape around it. Insects were especially important because they could exploit recovering vegetation while remaining small enough to live on limited resources. Their return provided nourishment for surviving mammals and birds, reconnecting parts of the food web that had been reduced to its narrowest threads. Plant recovery, therefore, became more than a botanical event. It was the first rebuilding of an energy pathway that could support increasingly complex communities. The fern signal did not mark an instant restoration, it marked a beginning. Fossil evidence shows that flowering plants, early conifers, and recovering forest structures appeared above the fern-rich layers as ecological recovery continued. The interval was measured in tens or hundreds of thousands of years, allowing different communities to return at different speeds. That sequence has a beautiful biological order. Light had to return enough for plants to grow. Plants created food and habitat. Insects followed the new vegetation, and small animals could then make use of those insects and the expanding plant material. Larger plants gradually reclaimed portions of the landscape, creating room for more complicated communities. The fern spike, therefore, represents more than an abundance of spores. It is a timestamp for the moment when Earth began producing new growth again. After the long interruption, the first green organisms did not rebuild the old world. They began a different one small patch at a time. Across the continents, a single narrow horizon joins places that seem to have nothing in common. It appears in Danish cliffs, roadside exposures in New Mexico, deep ocean cores from the Pacific, and sediment preserved in Antarctica. The surrounding landscapes differ completely, yet the same chemical signature rests at the same moment in geological time. It is a thin clay layer marking the boundary between the Cretaceous and the Paleogene. Sediment buried the line before erosion could erase its signature. The clue is iridium, an element present only in tiny amounts in Earth's crust. During the planet's formation, much of its iridium followed iron into the deep interior. Asteroids, by comparison, commonly contain far greater concentrations. When geologist Walter Alvarez and physicist Luis Alvarez examined the boundary layer in 1980, they found iridium concentrations roughly 30 times higher than those in the surrounding rocks. The discovery transformed a strange geological detail into evidence for an event occurring beyond the surface of Earth. Fine material from the impact had risen high into the atmosphere, mixed with particles already circulating above the continents and oceans, then spread around the globe. As that material settled, minute grains carrying iridium became part of the sediments accumulating on the seafloor, across floodplains, and along ancient coastlines. The layer became a chemical timestamp, preserving a trace of extraterrestrial material alongside the terrestrial debris of the catastrophe. Its importance comes from its reach. A boundary section in one region could once have seemed like an isolated curiosity. Finding the same iridium enrichment across widely separated continents changed the scale of the evidence. The event recorded in those rocks was planetary. The dust had traveled through the atmosphere far beyond the place where the impact occurred, leaving a signature that could be recognized thousands of miles away. Geologists can then compare that horizon with fossils, pollen, spores, sediment changes, and other chemical signals above and below it. The boundary becomes a reference point through which biological disappearances and environmental changes can be arranged in sequence. Extinction layers, recovery signals, and shifts in sediment chemistry can be measured against the same thin marker, allowing researchers to connect events that occurred across oceans and continents. There is something intimate about the physical record. Where the boundary is exposed, a person can stand beside a cliff or road cut and see the transition directly. A fingertip could span much of the layer. Below it lies rock deposited during a world dominated by Cretaceous ecosystems. Above it begins a geological interval shaped by their collapse and the gradual reorganization of life. The layer is small compared with the event it records. Three-quarters of Earth's species disappeared around this boundary, while the geological evidence for the impact itself occupies only a narrow horizon in stone. Its thinness reflects global dispersal. The material did not remain concentrated near the impact site. It became atmospheric fallout, distributed across the planet before settling into sediments. After 66 million years, the boundary remains readable. A chemical element that was once almost invisible within ordinary rock became a marker for one of the greatest biological turning points Earth has preserved. The catastrophe lasted far less time than the layers surrounding it, yet its signature crosses the planet as a single line, connecting distant stones to the same vanished world. The landscape of late Cretaceous India carried a wound of its own. Across what is now central India, enormous sheets of basalt had been pouring from fissures for roughly a million years before the impact. The eruptions formed the Deccan Traps, a volcanic province built through repeated floods of lava. Each episode spread molten rock across broad regions, then paused, only for another pulse to follow. The process was immense in duration, yet its influence reached far beyond the lava itself. Those eruptions also altered the atmosphere. Volcanic gases included sulfur dioxide and carbon dioxide, substances capable of changing temperature, rainfall, ocean chemistry, and the balance of ecosystems. Sulfur dioxide can contribute to cooling when it forms reflective particles in the atmosphere, while carbon dioxide exerts a longer-lasting warming influence. The Deccan system therefore acted as a persistent source of climatic disturbance while life was still adapting to its presence. Geological records suggest that some marine and terrestrial communities may have experienced changes in diversity during the interval leading toward the extinction. The evidence is complicated because ecosystems naturally fluctuate and the fossil record is uneven. Some researchers have found signs of ecological stress before the impact, while others emphasize that the strongest biological losses cluster tightly around the impact boundary. The disagreement matters because it changes how scientists understand the resilience of the world that entered the winter. Imagine a biosphere carrying several small burdens for generations upon generations. Species were already responding to changing temperatures, atmospheric chemistry, and volcanic pulses in some regions. Then another disturbance arrived with extraordinary speed. The impact did not have to create every weakness from the beginning. It entered an environment where some systems may already have had less room to absorb additional strain. The volcanic story also continued after the impact. Lava kept emerging from the Deccan region, while gases continued entering the atmosphere. This created an unusual climatic overlap. The impact produced intense short-term cooling through atmospheric dust and sulfur compounds, while volcanic carbon dioxide contributed to a much slower warming influence. One process pushed temperatures downward, while another supplied a pressure toward recovery and warming across much longer intervals. The timing of the eruptions has become one of the most carefully studied parts of the extinction story. Radiometric dating and detailed volcanic sequences indicate that major Deccan activity occurred both before and after the boundary. Yet the exact contribution of those eruptions to the mass extinction remains debated. Some interpretations assign the volcanism a substantial ecological role, while others find that the impact explains the abrupt global collapse far more effectively. That distinction does not make the volcanic evidence less important. It gives the extinction a more textured setting. Earth was already experiencing geological change when the impact arrived, and the volcanic system remained active while the planet passed through its darkest climatic disruption. The two processes operated on very different timescales, one arriving in an instant, the other unfolding through repeated pulses across immense spans of time. The Deccan traps, therefore, belong to the story as a background pressure, a persistent geological force surrounding the great biological turning point. The impact delivered the sharpest disturbance, while volcanism helped shape the conditions around it. In the rocks of India, both histories remain connected, recording a planet whose climate and living systems were already changing when the asteroid crossed the sky. A map of the surviving world would have looked uneven, even while the catastrophe itself was global. Latitude, elevation, water depth, and shelter could change the severity of the same climatic disturbance. The winter reached across continents and oceans, yet its pressure varied from place to place. Those differences created refugia, regions where survival remained slightly more possible during the hardest interval, when food was scarce and environmental conditions were shifting together. Near the poles, ecosystems already lived with long seasonal darkness and substantial swings in temperature. Their organisms possessed biological responses suited to cold and reduced light, giving them some preparation that tropical communities lacked. Fossil evidence suggests that certain groups experienced somewhat higher survival rates at high latitudes than at lower ones. The difference was modest, yet mass extinction can turn a small advantage into a lasting lineage. Even a slight increase in survival can preserve a branch of life while neighboring branches disappear. Freshwater offered another form of shelter. Rivers, ponds, and lakes respond differently to environmental change than the open ocean surface. Their chemistry can fluctuate dramatically across seasons, while their food webs often receive organic material from surrounding land. Many freshwater organisms had evolved amid repeated changes in temperature, acidity, sediment, and water level. Such variability gave them a broader range of conditions they could tolerate when the surrounding world became chemically disturbed. Their resilience came from familiarity with change itself. There were also refugia measured in depth rather than distance. Burrows and underground chambers separated animals from the most intense surface heating and later insulated them from the cold air. Within these spaces, survival depended on access to whatever food remained available. Dead roots, insects, fungi, and other organic material became part of a low-energy network that could continue even while photosynthetic production remained severely reduced. Shelter mattered because it connected physical protection with a food supply. Far below the ocean's surface, another refuge existed in the form of stability. Deep water communities were separated from the sharpest disturbances affecting surface plankton. Temperatures changed more gradually, and the deep environment was buffered from some of the rapid chemical swings occurring above. Benthic organisms, living on or within seafloor sediments, therefore faced a different set of pressures from creatures dependent on the surface production that had collapsed. None of these places offered immunity. A refuge only changed the odds. A cold adapted organism could still lose its food. A burrowing animal could still face scarcity. A deep water community could still suffer when organic material from above diminished. Survival depended on several favorable traits meeting in the same place at the same time, while the surrounding system remained damaged. That geographic filtering shaped the life that emerged afterward. The survivors were not a random remainder of the old biosphere. They were disproportionately drawn from lineages accustomed to scarcity, environmental variation, shelter, flexible diets, or reduced energy demands. Conditions that had once seemed peripheral became valuable when the planetary center became unstable. Across geological history, evolutionary change often gathers at boundaries, margins, and difficult habitats. The Cretaceous Paleogene extinction provides one of the clearest examples. The places that had demanded flexibility from life for generations became places where flexibility carried unusual value. Refugia were never comfortable worlds. They were pockets where biology still had enough room to continue, and from those pockets, the surviving lineages entered the next chapter of Earth's history. The first Paleocene landscapes carried an unexpected emptiness. Where established communities had once occupied nearly every layer of the ecosystem, many roles now stood vacant. Large plant eaters were scarce. Powerful land predators were absent. Canopy specialists, broad ranging omnivores, and many other forms had disappeared. For mammals that had spent the previous ages mostly small, this absence created ecological space on a scale their ancestors had never encountered. At Coral Bluffs in Colorado, layers of rock preserve an unusually detailed glimpse of this transformation. Fossils from the first 300,000 years after the impact show mammals increasing in body size as plant communities changed around them. The sequence is measured in generations and sediments, allowing scientists to follow an ecological rebuilding process with unusual resolution. A small animal entering a newly available habitat could become the starting point for a lineage with a very different way of living. The changes extended beyond size. Even modest shifts in body form could alter how an animal gathered food, crossed open ground, climbed vegetation, or sheltered from predators. Those differences accumulated as populations spread into newly available habitats. Teeth reveal shifts in diet, while bones record changes in movement and posture. Some mammals became suited to feeding on newly expanding vegetation. Others explored insect-rich habitats or mixed diets. As forests and open plant communities developed, different body shapes became useful in different places. Evolution was working with a surviving collection of lineages, each carrying inherited traits that could now be tested against opportunities that had barely existed before. Many early Paleocene mammals eventually vanished themselves. They were temporary occupants of an experimental world, appearing for a time and then giving way to other branches. Their fossils show that the mammalian rise was not a single straight ascent toward modern forms. It was a branching process filled with dead ends, replacements, and short-lived experiments. The survivors of those experiments would become the ancestors of later groups, while countless other branches faded from the record. Some of the earliest stem primates appear within roughly 150,000 years of the boundary. Their presence marks an early expansion into ecological territory that had been difficult to access when larger animals dominated the landscape. During the following million years, other mammalian groups began taking on distinct feeding and locomotor roles. The changes accumulated through ordinary reproduction and selection, yet the scale of opportunity surrounding them was extraordinary. Across roughly 10 million years, the descendants of these survivors separated into lineages that eventually included the ancestors of whales, elephants, horses, bats, and primates. Each lineage followed its own path through changing vegetation, climate, geography, and competition. There was no predetermined destination in those early fossils. Evolution had no blueprint for the animals that would eventually fill the modern world. What the extinction created was opportunity through absence. Removing so many established competitors opened ecological space faster than mammalian evolution had previously experienced. Body size, diet, movement, and habitat use could diversify as surviving lineages encountered resources that had once belonged to vanished animals. The transformation was gradual in individual lives, yet immense when measured across geological time. The age of mammals, therefore, began as an ecological consequence of loss. The world that followed was shaped by organisms that inherited the openings left behind, and those openings allowed a small collection of survivors to become something much larger. A coastline can recover its shape, forests can return, and oceans can fill with new life. Yet extinction leaves a different kind of absence. Some forms disappear so completely that no later lineage recreates their particular combination of anatomy, behavior, and ecological role. The Cretaceous world carried many such forms, and their endings remain visible in the structure of life today. The great sauropods belong to one of the most extraordinary experiments in terrestrial evolution. Their immense bodies, long necks, and specialized ways of feeding allowed them to occupy landscapes in ways no living land animal can duplicate. Their disappearance removed an entire mode of being from the planet. Modern elephants, rhinoceroses, and other large herbivores occupy some broad ecological territory, yet none reproduces the architecture or scale of those long-necked giants. Above the ancient landscapes, pterosaurs filled the skies with another arrangement of anatomy. Some species reached wingspans of 10 meters, which is about 33 feet. They were flying reptiles, built around bones and membranes unlike those of birds or bats. Their extinction erased an entire lineage of powered flight, leaving no descendant behind to modify or rediscover that particular design. The seas carried their own losses. Mosasaurs and plesiosaurs occupied major predatory and hunting roles in Cretaceous marine ecosystems, and their disappearance opened spaces later occupied by marine mammals and other survivors. Whales eventually became major ocean predators and grazers in some regions, yet their bodies came from a completely separate evolutionary history. Similar function does not restore the lineage that once performed it. Ammonites make the absence even more tangible. Their spiral shells had accompanied cephalopods through roughly 330 million years of changing oceans and previous biological crises. Then their lineage ended. Modern squid, octopuses, and cuttlefish preserve the broader cephalopod heritage, but no living animal carries the ammonite architecture forward. A branch can leave relatives while still losing its own particular form forever. This is why biodiversity cannot be understood as a tally of surviving species alone. Life is also an accumulated library of structures, behaviors, developmental pathways, and relationships. Each lineage represents countless generations of small modifications preserved through reproduction and selection. When that lineage ends, its particular combination of possibilities disappears with it. A related organism may occupy a similar niche, yet the lost pathway cannot be reopened. The species erased at the boundary did not fail a contest against evolution. They encountered environmental conditions outside the range that had shaped their histories. Large bodies, specialized diets, complex food webs, and narrow ecological partnerships could become liabilities when the physical world changed across an entire planet. The loss therefore reaches far beyond the disappearance of familiar animals. Roughly three-quarters of Earth's species vanished, including lineages carrying more than 150 million years of accumulated evolutionary history. The world that emerged afterward contained forests, oceans, predators, grazers, and eventually familiar mammals, but those communities were assembled from a different inheritance. Recovery can rebuild complexity. It cannot rebuild every branch that once produced it. The modern biosphere is rich, intricate, and still changing, yet it is also the descendant of a world with permanent absences. Some evolutionary paths ended at the boundary and remain closed, leaving the history of life shaped as much by what survived as by what can never return. On land, recovery could be traced through returning plants and expanding mammals. The ocean followed another clock. Its surface had once been filled with microscopic organisms whose countless interactions supported nearly every higher level of marine life. When those communities collapsed, the damage reached far beyond the disappearance of individual species. An entire biological network had been interrupted. Plankton may be tiny, yet their ecological importance is enormous. Microscopic algae capture sunlight and build organic matter. Tiny drifting animals consume them, while larger organisms feed on those grazers. Carbon moves through this chain, nutrients circulate, and oxygen production depends heavily on its activity. The impact disrupted these linked processes across the upper ocean, leaving surviving organisms with a radically simplified system. The earliest survivors were generalists, organisms capable of tolerating broad conditions and using whatever resources remained. They could repopulate disturbed waters, yet their presence did not recreate the intricate communities that had existed before. A species can return to a habitat within generations. The specialized relationships surrounding it may require far longer to develop. This distinction appears in sediments deposited after the boundary. The interval, sometimes described as the Strangelove Ocean, records an extended period of extremely low biological productivity near the surface. Evidence from marine sediments indicates that the surface ocean remained severely depleted for hundreds of thousands of years. Far below the water, organisms adapted to deeper conditions experienced a different environment, allowing parts of the marine system to persist while the surface struggled to rebuild. As light became more consistently available and nutrient cycles recovered, plankton communities began to diversify. New species appeared, then new interactions formed among them. Each addition altered the available food for another organism, creating a gradual rebuilding of the marine network. Recovery therefore unfolded through ecological succession and evolutionary change rather than through a single return to the former state. The timescale becomes clearer when measured against human experience. Land ecosystems could develop new structure within hundreds of thousands of years, while comparable plankton diversity required roughly 3 to 4 million years. Some marine groups needed even longer. The difference reflects the special nature of the oceanic food web, where tiny organisms at the base support enormous communities above them. During those millions of years, the chemistry of the ocean was changing as biological activity returned. Carbon cycling strengthened, nutrient pathways became more complex, and new plankton forms altered the conditions available to their neighbors. The recovery was therefore both biological and chemical. Life was rebuilding the machinery that allowed the sea to function as a connected system. Modern oceans carry the inheritance of that long reconstruction. Their plankton communities are descended from lineages that passed through the boundary and from later forms that evolved during the recovery. The food webs surrounding them were assembled through millions of years of diversification, replacement, and adaptation. A surface ocean can look unchanged from above, even while its microscopic architecture has been transformed. The waters covering most of Earth today belong to a system whose foundations were rebuilt after the extinction. Its recovery began more than 66 million years ago, and the process stretched across a span of geological time that dwarfs every human history. The sea returned to abundance through countless small beginnings, each one adding another thread to a network that had once been broken. For millions of years before the impact, survival often depended on becoming exceptionally good at one way of living. A predator could specialize in particular prey, a herbivore could rely on a narrow range of plants, and a species could become finely tuned to the climate of its home. Such specialization could be highly successful when familiar conditions persisted. The winter altered that landscape so thoroughly that flexibility became a far more valuable inheritance. Food webs had fractured, temperatures had shifted, and sunlight had become unreliable. An animal adapted to one resource could find that resource absent. A creature dependent on a particular habitat could discover that its habitat had changed beyond recognition. Physiological specialization carried costs when the environment itself became unpredictable. Survival increasingly favored organisms capable of adjusting their behavior, diet, metabolism, and reproduction to conditions that offered little consistency. Small body size also became useful. Smaller animals generally require less food, can mature sooner, and can shelter in places that larger creatures cannot easily use. A modest mammal able to feed on seeds, insects, roots, carrion, or other scattered resources possessed several possible routes through a difficult season. None guaranteed survival, yet together they created resilience. The same principle favored flexible metabolism, allowing some animals to reduce activity and energy demands when food became scarce. Reproduction added another dimension. A lineage capable of producing generations relatively quickly could respond evolutionarily to changing conditions more rapidly than one whose members matured over many years. Selection could therefore work across more generations in the same span of geological time. Traits that once seemed secondary became powerful advantages, especially when paired with broad diets and tolerance for environmental variation. These qualities had existed before the catastrophe, especially among mammals and other small-bodied survivors. They had simply occupied a limited portion of the available ecological space. Once larger competitors disappeared, those traits became useful across a much wider range of habitats. Mammals could spread into roles that had previously belonged to reptiles and other dominant animals, while natural selection continued refining the combinations that worked best. The consequences reached far beyond feeding and shelter. Flexibility can also shape learning, memory, social behavior, and exploration. An animal that encounters changing resources benefits from recognizing new opportunities and adjusting its behavior. Across later mammalian evolution, increasingly complex nervous systems became associated with environments where adaptation required more than fixed instinctive routines. The lineage that eventually produced primates inherited this broader history of behavioral flexibility. Human intelligence belongs to that much longer chain. Language, technology, planning, and scientific reasoning arose millions of years after the catastrophe, through many intermediate stages and many unrelated evolutionary changes. Still, the capacity to respond to variable environments has deep roots in mammalian history. Our ability to alter behavior when circumstances change is part of an inheritance shaped by a world where adaptability mattered enormously. The winter, therefore, changed more than the list of surviving species. It changed the evolutionary possibilities available to their descendants. Every lineage carries a history of pressures that favored some traits over others. And among mammals, that history includes a profound episode in which flexibility gained an unusual advantage. The creatures that endured carried those qualities into a transformed world where selection continued to build upon them, generation after generation, across changing landscapes and climates. A survivor has no special appearance. In the years after the impact, the animals that remained carried on with the ordinary demands of being alive. A small mammal searched for insects among leaf litter. A crocodilian waded in a river where food still passed within reach. Ground-dwelling birds moved through patches of fern, taking shelter, feeding, and returning to the same places when conditions allowed. None of these creatures possessed a map of what had disappeared. Their world was defined by what they could encounter each day. The forests of the earlier age existed only as absence, a condition they could never recognize as absence. There was no memory carried inside them of the former climate, no concept of the ecological order that had once surrounded their ancestors. For them, the altered atmosphere, reduced sunlight, sparse vegetation, and unfamiliar food web formed the only reality available. This matters because extinction is usually described from the perspective of geology, where layers mark boundaries and fossils divide one biological era from another. Life itself has no boundary stone. An animal does not cross into a new geological period and understand that it has done so. It eats when food appears, avoids danger, reproduces when conditions permit, and spends its energy wherever survival requires. The first returning ferns carried no message for the creatures moving among them. Their fronds offered edible tissue to some animals and cover from exposure to others. Spores spread across newly available ground, while insects gradually adapted to the recovering vegetation. Each interaction was local. A bird found an insect found a plant, a mammal found shelter. Through countless small encounters, a new ecological network assembled itself without any participant understanding the larger pattern. Somewhere within that reconstruction lived mammals belonging to lineages that would eventually produce primates. Their descendants would later develop increasingly complex nervous systems, social behavior, memory, and eventually the ability to reconstruct the catastrophe from fragments of rock. Yet the early animals themselves were concerned with immediate conditions. A patch of insects could mean enough energy for another day. A sheltered place could mean surviving another cold period. Their significance belonged entirely to the future. Even the end of the impact winter would have arrived without ceremony. Light would have strengthened as atmospheric dust diminished. Plants would have responded to the changing conditions. More insects would have appeared, followed by animals able to feed on them. The transformation would have unfolded through countless ordinary moments, each one too small to announce the passing of an age. Geology gives the transition a boundary. Biology experienced it as continuity. One generation followed another, with no surviving witness able to compare the altered world with the one that had vanished. The creatures living through those years did not know they had inherited an emptied landscape. They only knew where food could be found, where shelter worked, and when it was possible to move. Much later, stone preserved traces of those lives. Spores, bones, teeth, pollen, and layers of sediment became a record assembled long after the animals themselves had disappeared. Their world had passed without a narrator inside it. The evidence remained for minds that came much later, capable of looking backward and recognizing that ordinary survival had carried life across one of the greatest transitions in Earth's history. A lineage can be followed across deep time, one generation connected to another through anatomy, fossils, and inherited traits. Somewhere within that chain lived small mammals whose descendants would eventually occupy nearly every terrestrial habitat on Earth. Their story began in the altered ecosystems that followed the extinction, when ecological space had opened on a scale rarely seen in the history of complex life. Among those early mammals were animals belonging to the beginnings of the primate lineage. They were small, agile creatures, adapted to finding scattered food and moving through recovering vegetation. Their hands could grasp branches and objects, while their brains were relatively enlarged for their body size. These features did not announce the arrival of humanity. They were useful tools for animals navigating environments where conditions and resources could change from one generation to the next. As mammalian diversity expanded, those inherited capacities were carried into new forms. Grasping limbs became increasingly specialized in some branches. Vision, coordination, memory, and learning gained importance in animals that depended on movement through complex habitats. Each generation received a biological inheritance and altered it slightly through natural selection. There was no single moment when a future human appeared. The lineage accumulated changes across immense spans of time. The connection between that distant mammal and humanity is therefore biological rather than symbolic. The generations remained connected through reproduction, with each descendant carrying portions of the genetic history of its ancestors. Fossils reveal parts of this progression, while living anatomy preserves other traces. Hands, teeth, skulls, joints, and nervous systems all contain clues to the paths taken by earlier mammals. Much later, descendants of these lineages developed increasingly elaborate forms of communication and social learning. They learned to manipulate objects, preserve information, cooperate across generations, and eventually construct explanations for the natural world around them. Language allowed knowledge to outlive individual minds. Writing extended that memory further. Mathematics gave patterns a durable form. Scientific observation allowed distant events to be reconstructed from evidence that had remained in stone for millions of years. The strange connection reaches backward through every layer of that intellectual history. A human examining a fossil is using hands descended from grasping mammals. A scientist comparing layers of sediment relies on visual systems shaped through countless generations. A mind reasoning about an extinct world is the product of a lineage that passed through environments where flexibility had value. That does not mean the catastrophe was destined to produce humanity. Evolution contains branching paths, accidents, extinctions, and possibilities that never occur. The surviving mammals were not moving toward a predetermined destination. They were responding to each environment as it arrived. Human existence emerged from an extraordinarily long sequence of contingent events. Still, the genealogy remains. The creatures that endured the transformed world became ancestors of later mammals, and some of those branches eventually led to primates, apes, and humans. The same deep inheritance connects every hand holding a fossil to the animals whose descendants survived the ancient upheaval. Today, the evidence allows us to reconstruct that history with a precision unavailable to any creature living through it. Sediments preserve the sequence. Fossils preserve bodies. Chemical traces preserve environmental changes. Together, they let one surviving lineage look backward across geological time and recognize its own ancestry within the aftermath. There was no curtain rising over the recovering Earth. Light returned by degrees, filtered through an atmosphere gradually shedding the material thrown upward by the impact. As the silicate dust thinned, more sunlight reached the surface, and photosynthesis began its long return. Plants that had endured in scattered refuges expanded into exposed ground. Ferns gave way to varied vegetation, and each new layer created opportunities for insects, herbivores, predators, and everything connected to them. The continents themselves had scarcely changed their positions during those years, carrying the same broad geography into the recovering age. The oceans remained where they had been, and the chemistry of life still followed the same physical laws. What changed was the cast of organisms moving through those familiar settings. The great reptilian forms of the Cretaceous were gone. New mammalian lineages occupied spaces once held by animals with different bodies, diets, and ways of moving. Birds diversified into roles once held by other vertebrates, while flowering plants became increasingly important within recovering terrestrial communities. The difference became clearest in the forests that eventually returned. Their structure was assembled through millions of small, evolutionary adjustments, with plants competing for light and animals adapting to leaves, fruits, seeds, nectar, insects, and one another. Food webs regained complexity one connection at a time. A forest became a layered system in which every organism altered the possibilities available to others. The same rebuilding unfolded through the ocean. Plankton communities slowly diversified, restoring foundations for larger marine food webs. Fish populations expanded into newly available spaces, while marine mammals eventually inherited some ecological roles left vacant by extinct reptiles. The modern sea, therefore, carries a history written through recovery, with its present communities assembled from lineages that survived the catastrophe and those that diversified afterward. Across 66 million years, the consequences continued to accumulate. Whales returned to the water through a mammalian lineage that had once lived on land. Elephants developed immense bodies and complex social lives. Bats evolved powered flight and sophisticated ways of navigating through darkness. Primates developed flexible hands and brains, eventually producing creatures capable of measuring ancient rocks, reconstructing extinct climates, and tracing the history of the catastrophe itself. None of this was predetermined. Evolution responds to conditions, inheritance, chance, competition, and opportunity. The winter changed those conditions so profoundly that surviving lineages entered a new evolutionary landscape. Their descendants carried the consequences forward, generation after generation, until the world filled with forms that could never have occupied the same history before the extinction. The asteroid created the initial wound, while the prolonged winter transformed its biological consequences. 15 years of darkness and cooling altered which lineages could persist, which traits became useful, and which ecological relationships could be rebuilt. From that altered foundation came a different Earth. Today, the forests, grasslands, rivers, and oceans around us belong to that long aftermath. Every mammal, every bird, and every flowering plant carries some part of the history that followed the catastrophe. Even the human mind capable of reconstructing the event is part of the lineage shaped by its consequences. The winter ended long ago. Its legacy did not. It remains in the bodies around us, in the ecosystems supporting them, and in the living world that rose from the altered conditions of a planet after the darkness.